Hi, everyone. Thanks a lot for coming. I'm Alankrita. Hi, everyone. Thanks a lot for coming. I'm Alankrita. I just graduated from UCSD Electrical Engineering, and now I'm a research fellow here in the Data-Driven Decision Processes program. And today I'd like to tell you about a recent problem that I worked on, and towards the end also tell you a bit more about other problems that I'm interested in. So let's start off with the problem setting. And to motivate this, think about investing in a stock market where there are M stocks. And each day, at the beginning of the day, you need to choose a distribution over the M stocks that denotes how you are going to split your wealth to invest into each stock. So you could say, I'm going to allocate 1 over M fraction of my wealth uniformly into each stock, or you could say, I'm going to do 50% of my wealth on stock 1 and uniformly the rest over the others, something like that, right? And at the end of the day, what you end up getting is this vector of price relatives, where each component of this vector basically represents the value of each stock at the end of the day to that at the beginning of the day. So if, for example, xt1 equals 2, that means that on day t, the value of stock 1 went up by a factor of 2. And if you had $1 invested in it, it's now worth $2. And on the other hand, if xt1 is half, then that means like the value went down by half. Right. And I want to say that this general setting encapsulates the special case of betting on a sports match, or as the original example went, betting on a horse race, where each day there's going to be just one winner, and the only money you get back is what you invested in that particular horse. This is a very important special case. We'll come back to it later. And we can see that the ratio of your wealth at the beginning, at the end of each day to that at the beginning of each day is A transpose XT, because this is just the fraction you had invested in each stock times how much that stock value rose or depreciated, just add it up over all stocks. So this is the ratio of your wealth for one particular day. And what you want to do is invest sequentially over N days, which entails constructing this portfolio selection strategy, which is basically a collection of functions that on day number t takes the price relative vectors of days 1 through t minus 1 and tells you how what fraction of your wealth should you invest in each stock. So on each day, you get a probability distribution over 1 through m. And if you sequentially invest over n days, the ratio of your wealth finally to on day number 1 is just the product of your ratios each day. And then it turns out to be this value. And what you're hoping for is that this SN is large, right? So perhaps the simplest example of a portfolio selection strategy is the so-called constant rebalance portfolio, or CRP, which assigns which assigns the same fraction of your wealth to a particular stock each day. So this is completely time invariant, right? So this is one of the simplest examples of a portfolio strategy you could have, right? So now let me go on and exactly formulate the problem. So this was the definition of CRPs. And we can argue separately that CRPs are a very reasonable benchmark class to compare yourself against. So a reasonable goal that we can set for ourselves is to create a portfolio strategy that achieves wealth that's comparable to the wealth of the best constant rebalanced portfolio in hindsight, even for the worst possible case of market vectors, right? So this is the portfolio regret for a strategy A, and what you want is that this regret should be small. And we can write this in another form by writing down what SN is that might be more familiar. This log of product just becomes sum, and what you end up getting is this equivalent form, which looks more like an online learning problem against the best fixed action in hindsight for the worst possible case of inputs. And the loss function here is this special kind of loss, sometimes called the log loss. And so this is just online learning with this loss. Okay, so that was the problem formulation. Let me now tell you about Tom Cover's solution to this problem called universal portfolios. And really the crux of this idea is to use the relationship between gambling and data compression. More precisely, we use the fact is that sequential portfolio selection is equivalent to universal compression, Let's look at this equivalence a bit more closely. So how do you go from a universal compressor to a universal portfolio selection method? It's by something called probability-induced portfolios. And how you go from portfolio selection method to a universal compressor is by inputting these extremal Kelly price relatives, which are basically, it's a price relative that's one at just one component and zero everywhere else. So if you remember slide 1, this is the case when you're betting on a sports tournament and each day just one team is going to win. So portfolio selection with these input vectors turns into universal compression. And Cover shows us that in some sense, the most difficult market that you can deal with, the worst sequence of price relatives you can deal with is when everything is in the form of a Kelly vector. So gambling on a horse race is the most difficult stock market to deal with. Even more precisely, the equivalence is that portfolio selection against the best CRP is exactly the same as a universal compression of an Emery sequence against the best fixed IID probability, right? And so Cover's strategy that makes a probability-induced portfolio out of a universal compressor is able to achieve half log n times m-1 regret, which is optimal, including the constant. This is unsurprisingly also the optimal redundancy that you can achieve when you're trying to compress an Emery sequence against the best IID probability. Right, so this was Cover's universal portfolios. So now I'm going to complicate this problem a little bit and tell you about what we studied, which is the case when at time t, in addition to the yesterday's price relatives, you have some extra side information zt that you can incorporate. So this could be anything. A canonical example that is usually given is the truncated history of the market, but it could even be something additional, like in Cover and Ordentlich's original example, it was how oil prices might affect the stock market. If you're betting on a cricket match, it could be the condition of the pitch on a particular day, anything. So we also assume that there exists a state function G that maps the side information to one of S states, right? And this state function is not known to the investors. So you don't know how the side information is going to map to a state. And this is what makes this work different from Cover and Ordentlich's portfolio selection with side information, because they consider the case when the state is directly visible to everyone. So there's no function G in that case. Okay, so in this case, we can also strengthen the benchmark and allow it both the flexibility to choose and know the state function G, and also to play a state-wise CRP. So earlier, the benchmark was restricted to using the same vector at each, the same CRP at each time step, but now the CRP is allowed to adapt to the state in this manner. And we can have this regret formulation in this case, which is very similar, except that over here we have best state-wise CRP, and here it's your portfolio incorporating the side information, right? And perhaps this is a very simple example of a strategy that, a benchmark strategy that can adapt to side information is when you just look at yesterday's price relatives and decide the state according to that. So for example, you could say that if yesterday's price relative for stock 1 was 1.5, then today I'm going to invest 80% of my wealth in stock 1. Otherwise, I'm going to just do uniformly at random everything. So this is one example of how you could incorporate state into this problem. So let me just state our main result in words. So if the following conditions are met, so firstly, if the side information process is what I've written here as stationary plus, because it's almost the same as stationarity, a little more stringent, but quite close. So if this first condition and the second condition that the class of state functions has finite Natarajan dimension, which if you haven't heard of, it's just a generalization of the VC dimension to function classes that are supported on more than 2 outputs, because in our case, we might possibly have more than 2 states. So if these 2 conditions are met, then we're able to construct a portfolio selection strategy that achieves sublinear expected wealth ratio, and the exact non-asymptotics depend on the nature and properties of this process Zn. Right, so that was one problem that I've worked on. So before winding up, let me just tell you real quickly about other topics that I've worked on previously. So I worked on various topics in information theory, including universal compression, sequential prediction, portfolio selection, and so on. Information measures, which is about understanding fundamental properties of entropy and mutual information, polar codes, and so on. And I'm super excited to be here and learn from everyone about more topics in sequential decision-making. So very related to this presentation, one topic that I'm very interested in is understanding online learning-based methods for sequential prediction and exactly how they differ from compression-based methods in sequential prediction. And I'm very interested in understanding how we can incorporate important considerations and constraints like fairness and privacy in sequential prediction. And more generally, I'm very interested in understanding exactly how information theoretic methods can help us achieve more understanding of data-driven decision processes. So yeah, that's my presentation. Thanks a lot and happy to take questions.
Yeah, thanks for the very clear talk. Any questions?
Let's see.
So you mentioned this analog between gambling and compression, which was super cool. Had never seen this before. Is there an analog to compression when in the presence of states? You mentioned the history, so maybe that's part of it.
Yeah, that's what we take the same approach of reducing it to a problem of data compression with side information. So yeah.
Okay, cool. Thanks.
Thanks for the great talk. I really enjoyed it. Could you give some like real world examples of side information, like the Z variable you described?
Yeah, so you could have something like, so by real world example, you mean like real world or
no.
mathematical? So you could have
real
something,
world for us.
You could have something like this. You could look at, so for example, let me give you an example in which these conditions are satisfied. So let's say the market vectors are K Markov, and the state maps from the past K vectors, the past K market vectors to something. In that case, these conditions are satisfied, and you can, have a, compete with the benchmark that knows the state. So that's one example. You could look at something like this. You could looking at whether yesterday's price relatives lie in a certain rectangle or not. And that's also acceptable class. And in real life, like Cover's example was like oil prices. I don't know much about that, but if you're gambling on cricket, you can, know whether any players have any injuries or something like that. Yeah.
Thank you very much.
Yeah.
Okay. Thanks. I can take further questions offline. Thanks again. Next speaker can set up.